then I'm going to show you these two calendars. I also want to mention that down here at the bottom, you can see these are your last two homework assignments, and they are homework this time. So rather than having you do the assessments for more quiz grades, we've had quite a few quiz grades this term, so but we haven't had very many homework assignments. So I just decided to have you do the work section. Because it's the work section, you can correct it as you go, and your grade will be just your corrected percentage. So you should be able to get 100% on both of these assignments, and therefore, if your homework percent isn't 100% right now, that should boost it up a little bit. So those will be your last two homework grades, those two positive physics ones. I was going to make 14 due this week and 17 due the week after break, but a lot of students said they had a lot of tests and projects this week. So I just decided to make them both due after break. So if you don't want to have work to do over break, then you should focus on trying to get unit 14 done now. Okay. You should try to focus on getting unit 14 done this week. Then you can take the break off. And then when you come back, you can do unit 17 because it's due towards the end of that week. So let me show you those different calendars on where they're at on Axis. The one calendar is actually, like I said, posted on the door here as well. So for those of you coming to campus, you'll be able to see it there. But looks like it's gonna make me refresh here. Now I refresh, but log in again. All right, here we go. So here is the calendar of main events. So it doesn't have the assignments on here because the assignments are on the assignment calendar. I figured I didn't need to repeat that. But if you want to see exactly what's happening all 4 weeks after spring break leading up to that exam, the first day we're back, we'll be just touching in on pendulums with simple harmonic motion. And then that Wednesday, so that's A day, B day. And then Wednesday for A day, we'll be doing an FRQ review. And then for Thursday and Friday, A day, B day, we'll just be doing more general review, FRQs, multiple choice, variety of things. And then the following Monday, Tuesday, for those that aren't seniors, we'll just continue to review. I just wanted to make that a review day because that's senior retreat. So if you're not going to be here, I didn't want you to miss anything new. It just, you'll miss out on the group review, but everything is available to you to do the review on your own. And then that Wednesday will be B day's opportunity to do the FRQ review. And then we take our final exam. So on the Thursday and Friday, A day, B day, we'll be taking the FRQ portion. If you're here in person, you'll be taking it on paper. There will be 4 questions, 2 short and 2 long. So I'm dropping off one of the short questions. It's normally 5. I'm dropping off one of the short questions. They say the short questions are supposed to take you 13 minutes. So by dropping one off, that makes it under the 80 minutes. So 80 minutes should be sufficient for you to get those 4 questions done and feel the pressure of needing to get it done in a timely fashion, but not cutting you short. And then on the Monday, Tuesday after for A day, B day, we'll be doing the multiple choice portion, and it has 45 questions instead of 50. So it's also trimmed down a bit to better fit our 80-minute limit. Those grades will be heavily curved. They will be averaged together 50%, 50%. So FRQ will be half, MC, multiple choice will be half. And that will be your final exam grade for this class. So then the 2 class periods after that, so the Wednesday, Thursday at the end of April, and the Monday, Tuesday at the beginning of May for A day, B day in both cases, we'll be reviewing more and specifically using those exams to review. So you'll have them back and graded by that point, and you'll be able to see what you missed, why you missed points, why you earned partial credit, ask questions. It'll be a chance for you to make sure it was scored properly, but also just to review for the actual exam on May 5th. And then May 5th is the big day. For those of you taking it here on campus, which I imagine will be the majority, that'll be May 5th. It's in the afternoon. So that morning there will be no classes, but I'll be present in case you want to come on campus and ask questions. I suppose I could have a Zoom running as well. So you could just log in at any time, but there won't be any classes that morning. And then at noon is when you start the exam. And then after that, there will be, like I said earlier, no more assignments. And so it'll just be optional work from that point on. I know the rest of that week and the following week, many of you will be taking other AP exams that'll be in and out anyway. And then after that, there's only another week before we get into exam weeks. So it'll just be optional work at that point. So once you get through May 5th, if you're happy with the grade you have at that point, you won't have any more work to do for this class. You'll have everything done.
So what will we be doing in class after the exam?
It'll only be optional. So if you want to come in and do some optional work, you'll be able to do that. And if not, you won't need to be here.
Oh, so we won't have class, like we don't have to go to class?
Yeah, that's correct.
Oh, okay.
It made a new policy this year for this year only, that because we've had to go at such a different pace and been in a school, out of school, that once the exam is over, we don't have to hold class. And so I'm just going to make it optional. So if you need to do things to boost your grade or you want to try some of the labs, we'll probably have much smaller groups. So for people that just need to be on campus because they can't get transportation or whatever, I'll still be here with, options for you to do. But you could also just do study hall or whatever. So after May 5th, unless you're not satisfied with where your grade's at, you'll basically be done with this class. Yeah, Mark?
If the final exam is kind of what's holding my grade back, will we have a chance to do like corrections or something?
Yeah.
Okay.
Yep. It is heavily curved, but if it's still lower than what you need it to be, because it's 20% of your grade, so it's not huge, but it's also bigger than homework or quizzes. So if that's the biggest thing, then you'll still have an opportunity to do some corrections on that.
What are homeworks and quizzes worth again?
10 and 10.
And then the lab is worth 20?
30.
30, okay.
Yeah. All right. And then if we look at the assignments, just so you can see exactly when things are due, look at the map or the month view. So if you look here in April, this week there's nothing due. Like I said, I was thinking about making this Unit 14 due this week, but then decided since it's such a busy week for so many people with homecoming and a lot of projects and tests, I just decided I'll give you the break if you need it. So you could just finish it up over the break if you need to. But if you get it done, you get it done. You don't have to worry about it. And then Unit 17 will be due at the end of the week we come back. And so Unit 14 is on momentum. Unit 17 is on simple harmonic motion. And then the only test you'll have is also on positive physics. And it is a test grade, not a quiz grade, because it covers multiple units. It is an assessment type where it'll be the average of your original and your corrections %, but it will also be one of those things where you can kind of do it at your own pace. We won't do it that day in class. We'll just be reviewing because that's during senior retreat. It just needs to be done by that day. So it's actually open now. You could start taking it whenever you want. Yeah, Jackson.
What unit is this for?
Well, it's over all the units. So it's called Unit 23 on positive physics, but and if you click on it, you can see the details. So
thank you.
In the description, it shows you that's Unit 23 exam review.
And you said it's open now.
Yeah, it's open now, so you could actually start looking at it. It just has like one question on circular and one question on torque and one question. It's like just a bunch of variety of questions. Yeah. So and you'll have gone through almost all the units on positive physics by then. And so it's just a matter of taking the time to go through and do it and put it in as more of a test grade. I decided since it was over it's a little bit longer, it's 30 questions. So it's not huge because some are vocab or just picking a word and some are just other drop-down menus, but it's a little longer than most of our other assessments. And so I decided to make it a test grade because it was cumulative. Yeah, Mark?
Is it just from this semester or is it like last semester as well?
It's all year.
Okay.
Yep, all year. Pretty evenly balanced. It's about half and half each semester. So it's also good prep for the exam.
Is that how the AP exam is? Is that half and half?
Yeah, roughly.
Okay.
It's for this year. It's hard to say because we are supposed to have 2 other units we haven't even covered this year because we didn't have to. So it might not quite, it might be a little more heavy on the first semester.
What units were they, if we did cover them?
Waves and electricity.
Oh, okay. I know we learned about electric force. Do you think that's gonna still be on the exam?
That's the hazy one. That's why I went ahead and taught it. And then also with waves, I taught you just a little, when we did kind of an intro to the thing bouncing back and forth, the spring, mass on a spring, that was simple harmonic motion. And we'll do it again with pendulums on that Monday after break. It kind of has some wave connections, but I think what they're saying is there's no specific wave formula or sound content, but you still have to know simple harmonic motion because that unit is still covered. So I'm just trying to make sure that anything that's possible on the exam, we make sure we cover it.
Our tests were 30% of our grade?
I believe so. I have to look back at the guide, but it has it on that curriculum or class CMP, classroom management plan. The exam is 20%. I did look that up just to make sure I remember that correctly. The other breakdowns are a little hazy.
Will the final exam be via positive physics or will it be paper?
It'll be, for those that are in person, it'll be paper. For those that are not, it'll be download. So it won't be positive physics.
Okay.
Because I want it to be like what you'll experience on the 5th, as much as we can. If you're able to come on campus for that, I think, especially if you're planning to come take it on the 5th, I think it would be in your best interest to try to do that, but I understand if you can't. It's not, I mean, it'll be available either way. Obviously, for those of you like Jenny, you obviously can't come to campus, so, and I know there's some others that due to health and family issues, they can't either. So it's definitely available to take online, but it will not be positive physics. It will still be the same type of format as what you'll see on the 5th. All right, any other questions? We good with that? All right, so at the end of the last class, we were working on energy and work and power problems. And we didn't, I think you guys were pretty much done with your groups and kind of figured out what you need to do. I need to give you maybe just a couple minutes to get back with your groups and make sure you're ready to present. And then we'll have each group explain their problems from worksheet 3, which was on energy and work, and worksheet 5, which was on power. So Atticus and Roy and Jenny, you guys ready with question number 1 for us? Let me go ahead and show the question here to the rest of the class.
It's not on.
Where did it go? Oh, I must have accidentally deleted it. So if you can read it to us, I guess, because I thought I had it on the screen.
Wait, what's the third one you wrote? I can't.
I'll go ahead and have you guys explain the question and then you can demonstrate it however you like.
Okay. I'm sorry. I literally can't hear a single thing you say through this thing.
I guess I can read the question. So basically a volleyball is thrown straight up and it's leaving the player's hand, storing 81 joule of kinetic energy. And if 1.6 joule of energy is transferred from the ball to the air as it travels 11.2 meters upwards before reaching its maximum height. And then we have 2 questions. So Roy, do you want to share the screen?
Sure, I can like screen share. Okay. So it's a little bit difficult to read, but so for our energy equation, we have I wrote W net, but it's like net energy equals gravitational potential final plus final kinetic energy minus like initial potential minus initial kinetic, and then so basically. Sorry, my screen is kind of glitching. I don't know what's going on, but like basically, so for negative 1.6, that was like the like total dissipated energy. So it's like negative, like the energy traveling into the air, and then we don't know like what we're trying to find gravitational potential final, and then the initial kinetic is 0 because it's like it doesn't have any initial kinetic energy, and then the potential, initial potential is 20, and I think that was given. And then the initial kinetic was 81, and I think that's also given. So then basically you just like subtract everything, and then add everything, and then you get the final gravitational potential energy being 99.4 joules. And then for part B, basically it was asking for like the average drag force. So we just took the 1.6, which is like basically like the dissipated energy or like the drag force, and then divided by 11.2, which is like the distance that it went upward. So that would be like the average, and then so it would be 0.14.
You have do any of you have a picture of the graph, how that looks when you fit it together? You could share?
Yeah, I mean, I can like pull it up. I think I have the thing open.
Or Atticus or Jenny, I don't know if either of you have it easily available.
I don't have a PDF ready. We
You do,
were
or
also having, we weren't 100% sure how to do the system flow part of
Okay.
the chart.
Okay,
Sorry, can you see this?
yeah, it's opening.
Okay.
Yeah, here we go.
So I mean, for like the bar charts and stuff, basically initially we had like mostly gravitational and like a little bit kinetic for like the energy, and then sorry, no, it was the other way around. It was mostly kinetic because it was like the 81, and then like a little bit gravitational. And then for the final one, we basically had like these kind of inverted, like it was just basically all gravitational because like the kinetic is like no longer there.
Yeah, and then the last little bit's that dissipated part.
Yeah.
Okay, so large kinetic, small EG on the left, large EG, small ED on the right.
Yeah,
that
so,
correct?
but we weren't too sure about like the system flow.
Okay, so for the system flow, that's something I wanted to talk about anyway. So since you have EK in the beginning, 81 joules was given. That means the ball has to be in the system because the ball is what has that kinetic energy. And then you said there was also EG at the beginning, that 20 joules that was given. And that's not just the ball, because the ball can't have a gravitational force field by itself. There has to be the Earth as well. So you'd have to add the Earth in to your system in order to have gravitational. And then on the final side, the EG gravitational is now the majority. Like you were saying, and that's what you found. It ended up being 99.4. And you don't need to add anything because you already have the ball and the Earth. So those are already there and still would be what creates that EG. And then for the ED, that was given, it's only 1.6, so it should just be a small amount. And it's caused by the air because it says that's how much energy is transferred to the air. So it's basically drag. So you need to add air to your system. So it should be the ball and the Earth and the air would be the three things that would have to be considered for it to work like you described it.
Okay. Yeah, thank you.
Yeah. Anything else to add, Jenny or Atticus? Okay. For that final answer on part B, I don't think you had a unit on it, but just to make it clear, it was a force, so it should be 0.1 newtons. It looks like Roy's internet dropped out. Maybe that was why I kept flickering. All right. Any questions on number one, the volleyball question? All right, let's do question 2. As we're already starting to draw it, so maybe you can just live narrate as you're continuing, or maybe Carson, if you want to explain what you did, and then Haley, you can live explain and narrate and draw as you go.
So for this question, there's a roller coaster train at the top of a hill, and it has 42,000. So it starts at the top of the hill with 50 million joules. And then it rolls down the hill, and at the bottom it has 42,000 joules of energy, still of kinetic energy. And then it asks how much energy is transferred from the train to the track in the air, which is basically asking for the dissipated energy. And then it also asks for the combined magnitude of the drag and friction forces. Oh, wait, no. It gives us that, and then it asks the length of the track.
Okay.
So for our first graph, since the roller coaster started at rest, we just said at the top of the hill, all it had was gravitational potential energy. So that was the full bar. And then the second one, it lost all the gravitational potential energy because it was at the bottom of the hill now. And then it still had the 42 million joules of kinetic, which is why we drew it pretty high. And then we had the dissipated energy there as well.
And then we had the dissipated energy as combined drag and friction, and yep. And then, so because we know that work equals force times a distance, and we know that the lost energy is, or we know that there's 8 million joules lost, so 8 million, I'm gonna write million because that's faster, but equals 80,000 D. And so then if you realize that the
Can you click
distance,
on admit there to let him in? Thanks.
the distance equals 100. 8 million divided by 80,000.
And you said the answer to A. Can someone explain just how you get A, how much energy is transferred to the track?
We just started with the 50 million joules as the gravitational potential energy, and then if it ended with 42 million kinetic, the only other option, like in a graph, is the dissipated energy.
All right, and so it's just a difference between those two, right?
Yeah.
Okay. So a reasonably straightforward one. I would like to talk again about the system, but are there other questions before I talk about the system? So there's a couple ways to think about the system here. The way you've drawn it, you're showing, if you're showing it this way with the energy in the system, that means anything that caused dissipation should be in the circle, which would be the air and the track. That's air?
Yeah.
Okay, so air and the track. So those are both there, and it caused it against the coaster, which is there. So for this dissipated energy, everything's there. Because the air caused drag, the track caused friction on the coaster, right? So those three things had to be there for the ED. For the EK, the only thing that's moving is the coaster. And objects can have kinetic energy, they just can't have the other kinds of energy without being in a system. But they can't have kinetic energy by themselves. So it's just the coaster, and you already have that, so that's good. How about the EG?
Earth.
So we also need to add the Earth to our system, because you can't have a gravitational potential unless the Earth is part of the system, because the Earth is what creates the gravitational field between itself and the coaster. So that would complete the system. So when you're thinking about what goes in the system, you want to think back about, okay, which items would create these energies?
So then once you've put everything into the system, will they still need the arrow like pointing out?
Yeah, so that was my next point. So if you're going to draw the arrow coming out, that means some of that energy is leaving the system. And that's okay if you don't have this. You have to have one or the other, but not both. So if you draw the arrow, that means that drag, whoops, that drag and friction is the work that was done. And so if it's work, then you show it coming out, and then you don't need the track or the air as part of your system, because you're saying they're not in the system, so it's work. All right. So just wanting to make sure you're seeing the connections.
So we don't need to add drag and friction into there, we add an arrow out saying that's like work or whatever?
Well, you can do it one way or the other, you just can't do it both.
Okay.
So if you're gonna say that it's work, you put this arrow and then you take the track and the air out of the system because you're saying they're external now. And so these external air and track are what's creating the drag and the friction. But if they're in the system, then you do like they represented here, and you actually show, oh no, it was part of the system. That was just the dissipated energy from the track and the air. So you do it one way or the other, but not both. It's either work leaving and you don't include them in the system, or it's dissipated energy and you do include them in the system.
Okay.
That's usually the hardest part of these problems, is figuring out how the whole system things work. But the system actually carries over into the next concept of momentum. So I want to make sure we're pretty clear on it today. Good chance to practice it. Any questions from the group here or in the Zoom about this one? And you're seeing this work equals force times distance coming up pretty consistently. Very important part of it. All right, now we've got the killer whale problem. So the killer whale problem, I think that's already up here as well, right? Oh, they just got out of order. That's what happens. Okay. All right, here we go. Killer whale problem.
Okay, so in this question, killer whale is jumping out of water. It reaches the maximum. And at that point, the gravitational potential energy is just over 50,000 joules relative to the water surface. And then the whale, and after getting to the maximum and falling back down, it travels 20 meters, transferring 30 kilojoules of energy into the water. And then as it goes further, the gravitational potential is reduced to 20,000 joules. So the question was, is the whale still moving? And then how do you know? So just for the setup, on the left, you have the gravitational potential. And on the far right, I wrote the units just as a representation of the joules on the side. So the left, that's all 50,560 joules of gravitational potential. And that's when it's at the maximum height. So then for the system flow, we just included everything. So the earth, the whale, the air, and the water. So then to the right, you see the 30,000 dissipated joules, as well as the 20,000 joules of gravitational potential, and then a small amount of kinetic. So then,
Yeah. So then the whale is still moving at this point because it still has energy. Because it still has energy, after subtracting 30,000 dissipated and 20,000 gravitational, you're left with 560. And then if the whale is still moving, how much additional? 560 joules of additional energy must be dispersed for it to come to a stop.
Yeah,
All
very good.
leftover energy.
Yeah, really good. Yeah, clear. I like you've added a lot of detail. Got a good equation, good system flow. Yeah, I can't really think of anything to add. Any questions? Really nice job. All right. I guess the one question that you could ask yourself, how do you know that that 560 that's left over has to be kinetic? And probably most of you would catch this, but it can't be dissipated because they said how much that is, and it can't be gravitational because they said how much that is, and it can't be elastic because there's no spring or any kind of elastic object. So the only thing it could be is kinetic, and therefore it has to be moving because kinetic means movement. So, and that's what they determined. But just in case you weren't tracking that thought process of how do you know it's moving, that's kind of the thought process. All right, let's move on to the power questions. So who's got Jack and Jill? All right. So if you want to do the writing, Jackson, and then Frank, you can jump in and assist anytime needed.
Did I just use those?
Yeah, you can use either one of those. You can change the color of the ink or whatever.
All right, so the problem is asking about how much power is required. So before I do anything, I'm gonna write the equation. The power equals energy over time. And we already know the time, which is 5 seconds, but I'll get to that later. So for the system, in the beginning, in position A, there's nothing for like energy wise because there's like, it's at the bottom of the well, so there's no gravitational and there's no like kinetic, elastic, or dissipated. So that means, and at the end, there is a lot of gravitational because it got out of the well. So it went up. So there needed to be work, which was, so in the system, there is the bucket, there's the earth, and then there's work on it that's by Jill. So we need to figure out how much power she used. So we find the work that she has because energy is equal to work. So you have force times distance, and the force is equal to 12 kilograms times 10 meters per second, and then times the 10 meters, which gets the work, which is, wait, 1200, oh my gosh.
Yeah,
1200 joules. And then you put that over the time, which is 5 seconds, because you need the task to be completed in 5 seconds, and you get 240 watts.
Wait, is power the unit of joule or watts?
Watts,
Oh, okay.
because it's joules over second.
Yeah, yeah.
So, yeah.
Any questions? Anything to add, Frank?
No, I think he explained it pretty well, actually. Yeah.
I agree. Okay, yeah, go ahead.
Is there gonna be kinetic energy because she pulled up at a constant speed? It doesn't say anything about her movement at the end.
Correct. Yeah, so since it's at a constant speed, during that motion, it would be constant, but we're looking kind of before she was moving it and after she was moving it.
Oh, okay.
And so in that before and after, there wasn't any movement before she started and after she finished. So
Okay.
your conclusion was good. The only thing I would change is Jill doing work on the system, or is she taking work or energy out of the system?
She's putting energy in the system.
So we should just change the direction of that energy.
Oh, okay.
Yeah. That's the only thing I would change is, yeah, she's not taking energy from it. She's putting the work into it.
Okay, got that.
Yeah. Good.
Okay.
Any questions about that one? Let me show you just real quickly something you could do this a bit different. Mathematically, it doesn't really change it, but conceptually it could. You could put Jill in the system and declare that it's chemical energy. So that's just there to see for anyone who's had chemistry. If you've used those energy bar charts in chemistry, which I think our chemistry classes here at Oaks do those same things, then you may recognize, oh, chemical energy is energy stored in our muscles as calories, which can be converted to joules. So if you wanted to, you could do that. It doesn't really change the math of the problem. Most physics students would do what you guys did, and that's the way I set it up, as to say, Jill's doing work on the system. But just in case you're wondering, why is there suddenly ECH? We haven't really talked about that much. That's kind of a, hey, if you've had chemistry, maybe there's a little crossover you could notice here. But if you don't notice it, or if you've not had chemistry, it's not a big deal. The other thing I would say is this change in energy over time. I like the way that you recognize, hey, change in energy is the same as the work, so let's use the work equation. But we could have used the change in energy is going to be the change in gravitational potential, right? It had none at the beginning, and it has gravitational at the end. So we could use that equals mg times the change in height, because that would be how much the gravitational energy changed. And that's the same thing, right? I mean, it's the force is m times g, and the height is the 10. So it doesn't change the math at all. It's just more conceptually. If you didn't make the connection, oh, energy is work, which is force times distance, you could actually do it straightforward with energy and get the exact same results. So that's how closely interwoven energy and work are. They go directly hand in hand. All right, so both ways work equally well. I don't see an advantage to one over the other. Just wanted to make sure you could see multiple routes to solving this question. All right, and now we've got bulky and bulky. Did you have a question, Jenny?
I did.
You did or did not?
I did not.
Okay, you've kind of frozen, your hand was sort of in an upward position, so I couldn't tell if you're asking a question or if it just froze.
All right, so Hulky Bulky are two workers being considered for a job at the UPS loading dock. Hulky boasts that he can lift a 100-kilogram box 2 meters vertically in 3 seconds. Bulky counters with his claim of lifting a 200-kilogram box 5 meters vertically in 20 seconds. Which worker is more powerful? So powerful is like power is units of watts over seconds, and then watts is joules over second. And because energy and work are the same, we can find work by multiplying force times the distance. So for Hulky, we're going to multiply the 100 kilograms by gravity, which would be 10. So you get 1,000 newtons. And then you multiply that by 2 meters because it's force times distance. So you get 2,000 newtons over meters. And then for bulky, you will multiply 200 by 10, which gets you 2,000 newtons. And then you'll multiply that by 5 meters, which will get you 10,000 newtons per meter. And then he's going to talk about the other half. When he's ready.
So hard to write. So big.
Yeah, the bigger you draw, the easier it is usually.
5 meters. So bulky's using 10,000 joules, and Hulky's using 2,000. And then to find the amount of watts, we would divide that by the time. So for Hulky, it'll be 2,000 joules over seconds. That equals about 667 watts. 6 figs. I'm an eraser, so just deal with it. Here, got bulky. So then bulky is more powerful. Yep.
So the only thing I would say is make sure you show your equations. You show the work down, the net work equals net force times D. But then I would make sure you show the power equation as well. So that, because on College Board, if the equation's not there and just a substitution, then you'll lose some credit. Just making sure you include that equation for the power step. Yeah, I think everything looks good there. Finding the weight force, multiplying by the displacement to get joules, taking the joules divided by seconds to get watts. So who did more work?
Bulky would.
Yeah, Bulky did.
Because he produced the most amount of joules.
Yeah, Bulky did 5 times the amount of work, but he was so slow, he didn't have as much of a power rating. Hulky did 5 times less work, but so fast that it required a lot of power.
So which one do you think the UPS would have?
Good question. Probably Hulky because he's faster. Right? They got to get things loaded and unloaded quickly so they get their packages out. All right, any questions? All right, very good. So let's switch the share here. Go ahead and close this down. All right, so let's jump into the notes today. The notes are going to be on momentum and impulse. And then if we have time, we'll try a practice torque problem at the end. I want to save that to the end because we have been practicing that quite a bit. I want to make sure we do get through all the content and then we can practice at the end if we have time. I would like to practice more torque problems with angles because so far we've done all of them were perpendicular. So I do want to get to that, but we'll see how we can go through this other material. So if you're following along in your textbook and reading through the information in your textbook, you can include that chapter 9 in your reading. And you can see in chapter 9, it covers concepts of conservation of momentum, which will be a big part of today's lesson. And you can see it also covers center of mass, which will be more on Wednesday's part of the lesson. And then also collisions and impulse. And we'll talk about collisions, certain kinds of collisions today. And impulse, we'll talk about certain aspects of impulse today. But we will talk about collisions, impulse more on Wednesday. And we'll introduce the idea of center of mass on Wednesday as well as practice more torque problems, as well as practice more momentum problems. So that's what we have on tap. So let's first define what does momentum mean. And we kind of defined it before when we were doing angular momentum. So if you remember back in our rotational unit, the unit before this one, we introduced energy and we also introduced momentum. And now we're going to break down momentum in more full explanation. So we've got a spring exerting equal and opposite forces on two different objects that are initially at rest. So we're holding these blocks still and we're compressing the spring between them. So when we let go, that spring is going to push. It's the same spring pushing in both directions. So it's going to apply equal and opposite forces on those blocks, and the blocks are going to accelerate. Right? Whenever there's a force, forces cause acceleration. What does acceleration mean? Change in velocity. All right. So let's kind of walk that through mathematically. If we allow this spring to be released, those blocks will accelerate, meaning they will have a velocity. However, once they're no longer touching the spring, their velocities will stay constant. Because once they're no longer touching the spring, there's no force. No force, no acceleration. No acceleration, constant velocity. So there's going to be an acceleration as long as the spring is pushing, but as soon as they're not touching the spring anymore, constant velocity is the result. All right, so that's the scenario we're looking through. Now let's break that down mathematically with some equations and analyze what's going on here. Well, the force of the spring on block 1 has to equal the force of the spring on block 2 because it's the same spring. It couldn't push harder one direction than the other. It's going to push the same both ways. That doesn't mean the two blocks will respond the same. If block 1 has a larger mass, we can see the picture looks like block 1 would have a larger mass. What is that going to change? How will block 1 be different than block 2 if they have different masses? Yeah, the bigger mass will accelerate less, right? Same force, but bigger mass means less acceleration. Smaller mass means more acceleration, right? So their forces are equal, though. They're just going to accelerate differently if their masses are different. Therefore, their final velocities will be different, right? Because they have different accelerations. But the forces are equal. So if we think about Newton's second law, the net force on object 1 would be its mass times its acceleration. The net force on object 2 would be its mass times its acceleration. And if their masses are different, their accelerations would be different. But those forces are equal. So if we subtract them, they still give us 0. And we know that acceleration is change in velocity over change in time. So we kind of talked this through verbally a few minutes ago, but now we're just seeing it with expressions, equations. We know that the acceleration is Vf minus Vi over delta t. Now, we also know that in this scenario, they started at rest. So those VIs are all 0. And if you look at it mathematically, the time is the amount of time is the same. And the time would also cancel. If we set m1 times v1 over t equal to m2 times v2 over t, if we just added that second term to the other side of the equal sign, you might more easily see that the t's would cancel. But you could look at it this way, factor out the t, because both of them are divided by t, so factor out like 1 over t times those, and then 1 over t equals 0, so that means the t's cancel out. So you can hopefully see that the zeros for vi take that variable out, and the time variables cancel because they are equal. And what we're left with is m1 times v1 minus m2 times v2 is equal to 0. So we've got a new mathematical concept. And again, it's only sort of new because I introduced it to you weeks ago when we were learning about rotation and rotational momentum. And here was the equation for rotational momentum. I don't know if you'll be able to see it real well on the screen, or on the Zoom, but it's L equals I omega. So you can see that on the formula sheet. L equals I omega was angular momentum equals rotational inertia times velocity. Well, this equation is linear momentum with lowercase p as the variable equals inertia in the form of mass, because it's now moving in a linear manner, times velocity as v, which is linear. So this was all rotational. I was rotational inertia, omega was rotational velocity. This is all linear. Mass is linear inertia, and v is linear velocity. So just hoping you can make those connections to before what we were learning and now what we're focusing in on today. This equation is given to you on the formula list, so not one you need to memorize. It's about the 5th one down or so, right underneath, 5th or 6th. It's right underneath the acceleration, centripetal acceleration. It just says P equals mv. So it is on here. But it is one that you need to make sure you know how to use. So any questions about this equation, where it comes from or what it means? So it looks a little bit like Newton's second law, right? Force equals ma, but instead it's momentum equals mv. All right, so it's just a little bit of a different relationship. They don't go hand in hand, but we can derive this one from Newton's second law. In fact, we just showed on the previous slide how we derive it from Newton's second law. Now, since velocity is a vector, it will have direction. And that makes momentum a vector with direction, right? So here's a couple concluding facts about momentum. If we think about the scenario before the spring is released, we know that using this equation, our before and after picture, if we think of the momentum of the kind of lime green block and the momentum of the orange block on the right, they started at rest, so they both had 0 velocity. So before the spring's released, they have 0 momentum. They have inertia because they're mass, but they have no velocity, so 0 momentum. But after the spring is released and now they're moving with constant velocity, now we can see that the mass of 1 times its velocity minus the mass of 2 times its velocity would have to equal 0. They have to be equal, equal and opposite. So the total momentum of the system didn't change. It was 0 to begin with because it had no momentum at all. And now as a system, it is still 0. Does the lime green block on the left have momentum? Yes. Does the orange block on the right have momentum? Yes. But because they're in opposite directions and they're vectors, if we add them together, the system has 0 momentum. They cancel each other out. It's like balanced forces, balanced momentum. Okay, same kind of an idea. Any questions about that idea?
Would it be mv plus mv equals 0? And then the fact that it's a vector would make the second one negative?
Correct, yeah. So here they're just writing it as if this one is a negative vector because of its direction.
Okay.
Yep. So you can do it as plus a negative or subtraction, whichever makes better sense to you. All right, so here's another kind of word summary. We know that from what we've illustrated that momentum appears to be conserved, like energy and like mass. The total momentum of a closed isolated system is constant. The momentum in the before picture has to equal the sum of the momenta in the after picture, as long as the system is closed. And What that means is explained down at the bottom. A closed, isolated system is a system of objects with no external forces. So that scenario we just looked at wouldn't work if there was drag force, or it wouldn't work if there was friction. Okay, there has to be no external forces acting on it. And there are a lot of conservation principles that we've learned, and some that you've learned in other classes. And they all have limitations though. So for instance, if you've had chemistry, I know some of you have, some of you haven't. If you've had chemistry, you may have learned about the law of conservation of mass. We don't focus too much on that in physics, but in chemistry, it's huge. You use it for chemical reactions all the time. The mass of the reactants has to equal the total mass of the products. But that only works for chemical reactions. There's a limitation. It doesn't work for nuclear reactions. In nuclear reactions, some of that mass can turn to energy, and some energy can turn to mass. It's called mass defect. It's based on E equals mc squared. When we talked about energy, the total energy of the system is conserved, but depending on how we define the system, we may have energy leaving the system as work, right? So, and it's the entire energy, not individual. Like the kinetic energy doesn't have to be conserved, but the total does. So there's limitations there. The limitation here with momentum is there can be no external forces. If there are external forces, it won't be conserved. However, that's pretty easy to control, either by making our experiment very controlled, or just by saying, well, let's use objects that have very small drag, very small friction, and we can neglect it. All right, conservation of momentum. Now, another part that often will trip students up is they'll recognize there's lots of other forces within the system, but it's only the external forces that will change the system's momentum, not the internal ones. So if we look here, we see there's a force exerted by the rider on the handlebars, but there's a force exerted on the rider by the handlebars. So that's an internal back and forth Newton's third law relationship. Those cancel out. That force exerted by the tire on the road would be equal and opposite to the force exerted on the road by the tire. So remember, according to Newton's third law, forces come in pairs. And we even sometimes call them action-reaction pairs. But those are internal forces and they always come in pairs, so they cancel each other out. Those are not considered external forces. All right, so we can ignore all the internal forces and just focus on things that are external to the system. So when we were going over those worksheets, I tried to talk to you about, hey, what did you put in the circle? You know, what should be in this circle? If there's gravity, you've got to include the earth. If there's friction, you've got to include the track or whatever. You need to be thinking again about the system here. Well, what is my system? Okay, is that in or out of the system? If it's in the system, all the forces would be internal and we can ignore them. If it's out of the system, then that's going to cause a change in momentum because it's doing work on the system. So thinking about what's in the system continues to be a matter of focus here for conservation of momentum. This slide is basically just on a word that I see often in AP questions. And many students are familiar with the word recoil, but it's just an odd enough word that I've had students throughout the years say, hey, what does this word mean? They'll see it in a practice question or something, and they're not familiar with it. So I just want to make sure you understand that term recoil. If you've fired a gun before, if that's like one of your hobbies, then you know what it is. But if not, you may not. So recoil, an example of that is when you fire a gun, the bullet is there. We apply a force to the bullet, which launches the bullet that way with its momentum, and there has to be an equal and opposite force creating momentum for the gun going backwards, and that's the recoil. The bullet fires forward while the gun recoils backward. Another example would be firefighters. There's force pushing this water and giving the water momentum, but then there has to be an equal and opposite force creating momentum in the other direction. So if you've ever seen like a hose on the ground, not a fire hose, it's like a regular hose with a nozzle on it. If you turn it on high, it like flops around. Okay. Well,
Or like in cartoons when the guy like holds it and they fly into the air.
yeah, that's a little different since it's a cartoon, but same idea. But here you can see, actually, if you watch firefighters when they're manning the hose, there's never one person because there's a lot of force generating the momentum of the water. So there's going to be a lot of force backward, and normally that's going to be multiple people manning that hose to protect against that recoil. So if you see that recoil, it's just talking about that equal and opposite force backward, that equal and opposite momentum backward. And I just want to make sure you know that word so that if you see it in a question, it doesn't confuse you, because I've had enough students through the years just be unfamiliar with that term. All right, so let's kind of sum it up here. The concepts of momentum are useful for predicting the outcome of interactions between objects, such as collisions and explosions, which is what we're going to focus on here in the coming slides. As I mentioned earlier, momentum is a vector quantity. So it does have not only magnitude, but also direction. And the direction will be the same as the direction of the velocity. So same, just like forces, the direction of the acceleration is the same as the direction of the force. In momentum, the direction of the velocity is the same as the direction of the momentum. So similar relationship there. And then the last one, we've made some comparisons that, this angular momentum has some comparisons to this. It even looks a little bit like Newton's second law with force equals ma, and we can actually derive it from that. But it also looks a little bit like the kinetic energy equation, which also has mv, but it's 1/2 mv squared. And while those look similar, they are not related. Okay, so just want to make sure that you recognize just because there is a similarity in their appearance, it doesn't necessarily mean they're related. So is it related to force? Yeah, we can actually derive this equation from force. Is it equal to force? No, they are different concepts, but there's a relationship. Is it related to this angular momentum, L equals I omega? Yeah, it's inertia times velocity, same relationship. Are they the same thing? No, because this has to be rotating and that's linear. So, but there is relationships. Kinetic energy and momentum, there's no like kinetic energy momentum relationship. They don't really go together. Now, an object that has momentum will have kinetic energy. I guess you could maybe say there's that loose connection, but mathematically, there's no real connection.
Yeah, they kind of represent a similar idea almost, like how much.
Yeah, two different ways to measure motion. One is about how much energy it has, and one is about how difficult is it to stop. All right, now I have one of these cradles in here, but I know for those of you that are in the Zoom, it would be really hard to see. I've had a couple guys that were experimenting with that before class, but to make it easier for everybody to see, I've got a little video here to show. So when one ball comes in and collides, it shoots one out the other side. Kind of makes me dizzy.
Every Newton's cradle I've seen always ends up getting tangled.
Yeah, they do get tangled pretty easy. In fact, there's one that kind of has a knot in the string. So
That's really unfortunate.
Oh, you have one.
it still works, but so, and you can see when they were trying it over here before class, it would slow down because you can hear the sound, so it's losing energy to the surroundings, right? There's going to be friction in those collisions. There's air resistance and drag, even though it's going to be fairly negligible over time. That drag accumulates. So,
if the Newton's cradle was in the NASA vacuum that we saw that had no air resistance, would it just continue forever?
There would be friction still. There would be no ability to release sound because sound can't travel in a vacuum, and there would be no air drag, but there would still be friction.
Okay.
So it wouldn't go forever, but it'd go longer.
You just invented perpetual motion.
All right. So let's look at another example. Another thing we can't really simulate is being on the International Space Station. So we're going to watch this gentleman explain about momentum here.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. Since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving, it causes the other to move, or they're both moving and collide and move off in different directions. The total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. and that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So for example, if I can get these two to stick together, while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle,
But it'd be really hard to.
I'm just going to remain here. Since the total conservation, since the total momentum of the system has to remain constant.
Like, FML here, I'm just stuck in the middle of the room.
I'd be like, all right, we've had enough of you, Joe. You've gone to the middle.
The middle of the room.
Yeah, hazing on the International Space Station.
So you just shoot the food to them.
Because like, it'd be really hard to get yourself stuck there because of conservation of momentum.
Yeah, but if someone stuck you
But
there.
if somebody stuck you there, you're
Yeah.
done.
Like, we
It's
gotta
like
avoid
they
it.
gotta reach you out and like let go of you.
Yeah.
You're in a timeout.
Now, you could take off a shoe and throw it in one direction, because that momentum in one direction is gonna generate momentum in the other. You may have to start taking off a lot of clothes to get.
Start like spitting.
All right.
Those
You just
experiments
like a
always
t-shirt
make
on
me
the leg.
nervous.
Yeah.
When they do stuff with water and stuff in the ISS and there's like loose computer parts everywhere, I'm like so scared something's gonna explode.
All right, so we're gonna go through several examples here, and I'm gonna go through them pretty quickly. I wouldn't necessarily encourage you to try to write them down. It's gonna be kind of the same process over and over again, but looking at a bunch of different scenarios with mostly the same numbers, just you like changing one number at a time to make the scenario a bit different. But what we're gonna look at is what you'll see underneath this. It says the carts stick together. So in every scenario we're gonna look at today, they stick together. On Wednesday, then we'll talk about what if they don't stick together, what happens then. It's going to be the same relationship, but we're going to focus on one kind today. So here we've got a 2 kilogram object moving with 10 meters per second velocity, and it's going to collide with a 3 kilogram object that is sitting at rest. But we know, because of the conservation of momentum, we even saw it illustrated. I thought it was funny that like the very first time he put them, they stuck together, and then it took him like 4 times to get them to stick again. That'd be tricky. I bet that felt stressful for him trying to videotape that.
Like I'm missing up.
All right, anyway,
That's probably
so
like his fifth take.
So if we think about the before and after picture with our mathematical analysis of momentum, beforehand, we have the momentum of the orange block and the momentum of the purple block, and after they each have their own momentum as well, but they're stuck together, so they have the same velocity. So if we break this down, initially the orange block has a 20 kilogram meters per second momentum, and the purple block has 0 momentum. Afterwards, they're stuck together, so their velocities are the same. So we've got a 20 plus a 0 equals 5 times the velocity. If we divide that momentum by the mass, we find out that the final velocity, once they stick together, would be 4. So if one is moving at 10 and the other is moving at 0, it isn't necessarily going to be then moving at 5 because their masses were different. So we have to do that momentum analysis. Makes a little bit more sense. The one that was stationary was actually more massive. So that's why we end up with having less than half of the initial velocity. Now, if we look at another example where in this case, instead of the purple one being stationary, it's also moving just slower. And so the orange one catches up and eventually collides, and then they're going to continue moving to the right. So we can see one was moving 10 and one was moving 4, both in the same direction. So once they collide, we would expect the orange one to slow down and the purple one to speed up, right? So their final velocity should be greater than the initial 4 that the purple had, but less than the initial 10 that the orange would have. And we can prove that out mathematically with the same relationship, the momentum before and the momentum after. So the orange one still had 20 before, but the purple one now had 12 instead of 0. Afterwards, they still have their same masses and they would still have a common velocity because they stick together. And so again, we can take this 32 total momentum before divided by the 5 and they would have a final velocity of 6.4. So like we said, a little faster than the purple one was moving earlier, a little slower than the orange one was moving earlier. Questions on these first two examples? Yeah, Ethan?
What would happen if they didn't stick together?
That's Wednesday.
Okay.
You'll still do the same analysis, but we'll do examples like that Wednesday.
Sweet.
Yeah. All right, so here's one where they're actually moving towards each other, but this one has a momentum of 8 and this one has a momentum of 36. So they're not going to just stop. One has way more momentum than the other. So because it has so much more momentum, it's going to send the whole system moving in its direction. But the scenario, the way we work it through is exactly the same, the before and after picture. So we had 8 and 36, but the 36 you'll notice here, they have a negative 12 because velocity is a vector. Therefore, we end up getting a negative 36 momentum. But over here, they have a common velocity in the end, and we just added the masses, same on that side. So here we find out the final velocity is negative 5.6 meters per second. So in the end, the sign of the velocity tells us the direction it's moving. And we can logically think through what it should be, but we can also prove it mathematically. All right, what if they have 12, so 2 times 6, and 12, 3 times 4, and they're going towards each other? Well, logically, what should happen?
They come to a halt.
Yeah, they just should stop. And so that's what should happen. And mathematically, we can prove that. If we have 12 plus 12, but in the opposite direction, then that's going to give us a 0 on this side of the equation. And 0 divided by 5 gives us 0 meters per second.
So if that guy threw them like at the perfect, like exact same velocity, they would just like stay
They
there.
would just stop. Yeah. And actually, normally we are able to work in labs and handle equipment more. And so one of the things we would be doing probably today or next time would be getting those carts out and having you roll carts around. We're a little bit limited in what we can do with that. We may do a little bit of that on Thursday, but with the plexiglass up everywhere, there's not many places to actually get those.
Do it outside.
Yeah, we can do it on the ground and stuff, but so we may practice a little bit with that and give you a chance to try it out a little bit.
Yes.
If we have time.
If you put like Velcro between the Newton's cradle balls and you had 2 of them, you could like spread them apart and maybe
Stick together. And those carts that we have, some of them have Velcro, so you can get them to stick together. All right, now here's our last one, and this one looks like it's a little bit crazier of a scenario. We've still got our 2 kilogram orange one moving at 5. We've got this purple one, only 1 kilogram moving at 2 in the other direction. And then this 4 kilogram moving really slow to the right. And so we can actually have a system where we get multiple collisions and multiple connections. They're all still sticking together. And it doesn't matter how many objects there are, the same scenario works. What's the before, what's the after? Well, there were 3 momenta before, and there will be 3 momenta after. But because they stuck together, they all have the same common velocity at the very end. Now, we could find the momentum of just these 2, find that, and then combine it with third one. We could do it step by step, but you don't have to. You can do it all at once. And so like they're showing here, 10 for the first one, -2 for that one, 4 for that one. Afterwards, they all have the same velocity. So we just add the masses together and factor out the V. So 10 minus 2 gives us 8 plus 4. We end up with a momentum total of 12 divided by 7 kilograms. So they would have a velocity in the positive direction of 1.71 meters per second. So the equations will not change at all when they don't stick together. The only difference is instead of all of these having V4, they would each have their own velocity. And so you either have to be able to measure them or know the energy. You have to know a little bit more information to solve those kind of problems. But we'll focus on doing that on Wednesday. All right, the last concept, so just a couple slides here to wrap up, is the concept of impulse. And impulse is when you apply a force over a given number of, or given amounts of time. So when you hit a baseball, hit a tennis ball, kick a football, kick a soccer ball, any of those things, punch a punching bag, you're providing an impulse because you're applying a force over a given amount of time. If you want to maximize the impulse, you either have to maximize the force or maximize the time. So for instance, if you're a boxer, there's a limit to how hard you can punch eventually, right? You can only punch so hard. So, but if you can make the punch contact for a longer amount of time, you've increased the impulse. Okay, so So instead of like with karate, when I studied Taekwondo and karate earlier in my life, like when you break boards and stuff, you're supposed to envision going through the board. Okay, you don't stop at the board, you go through the board, right? You want to increase the amount of time where that contact is there to increase the impulse. All right, now there's also a concept called bouncing, but we'll talk about that Wednesday as well. All right, so if we apply a force, what does a force cause?
Acceleration.
Acceleration. What does an acceleration mean?
Change in velocity.
Change in velocity, all right? So if we recognize Newton's second law with those understandings of, hey, when I apply a force, it creates an acceleration, which means the velocity changes. You can see the substitution here that we looked at earlier when we were looking at momentum. But now we're going to take a slight twist. Let's combine the masses and the velocities, because now we know m times v is momentum. So now we got final momentum minus initial momentum all over t. Well, final minus initial momentum is just change in momentum.
Crazy.
Right? And change in momentum over t, if we just multiply both sides by t, we get what's called the impulse momentum theorem. And this one is also on the formula sheet. It's right underneath the P equals mv. They're just right here together.
That's cool.
This impulse momentum theorem is incredibly powerful for solving problems, a lot like the work energy theorem. If you can't find the energy, but you can find how much work was done, great, you know how much energy, because those are equal. If you can't find the momentum, but you can find the impulse, great, now you know the momentum, because they're equal, or vice versa. So just like the work energy theorem gives us a really powerful tool, knowing that they have to be equal, the impulse momentum theorem gives us a really powerful tool. Maybe we know the force and the time, but we don't know the mass and the velocities. No worries. Use force and time to get impulse. That will be the change in momentum. And then we can go through and find, if we know the masses, what those velocities will be. So this equation is very helpful. You can see here in the equation that they've got a lot of deltas here. So it's the change in momentum. Now, I don't know, again, on the Zoom, I know it's probably going to be hard to see, but the only thing I've changed here on the board compared to this is instead of saying sigma F, or the sum of forces, net force, times delta T equals delta P, I've just changed delta P to M delta V. So delta P is M delta V, and I prefer to write it this way personally when I'm solving problems, because often what they ask you to find is the velocity change. Or maybe the final velocity where you know what it started at. Maybe it started at rest or something like that. So I generally don't write it in this form, but this form is what's on here. Okay, so that's why I want you to recognize that. I would usually change that delta P to M delta V, if that makes sense. All right. Let's look at an example to wrap it up. So a 2 kilogram ball has a velocity of 3 meters per second to the right when an external force of 5 newtons, also to the right, is exerted on the ball for 4 seconds. So the whole time that force is exerted, what's going to happen to the ball? Forces cause acceleration. Right? So it's going to be accelerating for 4 seconds. If it's moving 3 meters per second now, and the force is in the same direction, later it's going to have to be moving faster, right? It has to be accelerated. And then B, find the impulse. Now, it's a little interesting the way they show the work here, because you can find A and B all in the same step. And here they break it down as almost 2 separate problems, but I think the reason is they want to focus on the units. So let's use this force times time equals change in momentum. Whoops, a little too fast. So we got the net force times time equals change in momentum, which means net force times time equals final momentum minus initial. So our force was 5 newtons. We applied it for 4 seconds. Our mass was 2 kilograms at some final velocity, which we're trying to discover, minus our 2 kilogram mass times its initial velocity of 3 meters per second. So if we solve just algebraically, we can find the final velocity is 13 meters per second. But if you'll notice, they've actually found part B right here. This is the impulse, right? F times T. And that's just 5 times 4. They've actually answered it right here. So while they were actually answering part A, part B is actually in the middle step right here. They have the answer for part B. You see that? Making sense? Now, on this next slide, they show part B solved separately, but I think it's because they're wanting to emphasize something about the units. If you look at this, the units are kilogram meters per second. Well, that is a typical momentum set of units. When they just go straight forward F times T, they write their units as newtons times seconds. Well, that is also the same thing. A newton times a second is a kilogram meters per second. The tricky part is, or maybe not tricky, but the thing that I want you to recognize is normally when they write impulse, they will give it to you in newton seconds. Normally when they write momentum, they will give it to you in kilogram meters per second. Those two units are equivalent, but they're generally reserved for these two uses. So if you put an impulse with kilogram meters per second, it's not wrong. You wouldn't lose points. But if they give you an impulse value, they're probably going to give it in this unit. So I just want to make sure you're aware of that they are equivalent in any and every way, but you'll probably only see it applied that way, or almost always see it applied in those two ways. All right, so that gets us to the end. Just enough time to get you started on a torque question. But first, any questions for this impulse definition or momentum or anything else we've covered today? Making sure we were on the last slide. I thought we were. All right, so let me go ahead and let's look at the torque problem I want you to try to solve.
Bulky and bulky.
All right, so you might have time to solve it, but I doubt if we're going to have time to go over it together. So I want you to try to see if you can solve it in these last 8 or 9 minutes, as much of it as you can. And then at the beginning of class on Wednesday is how we'll start. We'll go over this question. So you can see and this is on worksheet 2 again. If you still have that worksheet, we kind of keep coming back to it and practicing different problems. It's the third question on that worksheet that you want to use, that torque worksheet number 2. It says a uniform board is leaning against a smooth vertical wall, which is frictionless. So that's the smooth there is telling us it's frictionless. The board is at an angle theta above the horizontal ground. The coefficient of static friction between the ground and the lower end of the board is 0.650. Find the smallest value for the angle such that the lower end of the board does not slide along the ground. So if you've ever leaned something against the wall where you had a slippery floor, like a cement floor, you know, if you make it too angled, it's just going to slide out, right? You have to make it steep enough that it won't slide. That's their question. What is that angle where it's just steep enough that there's enough friction to keep it from sliding out? So even though there's an angle here, it's a little different. Follow your steps. Figure out your force equation. Identify your pivot point. Then analyze the torque. All right. So I'll give you these last few minutes here to see how much work you can get done. If you have any questions, you can ask them as you work, and then we'll discuss it on Wednesday.